Hello, everybody, and welcome to Weak Base Wednesday. Far more exciting and fulfilling than Wing Wednesday. Today, we're going to be looking at strong and weak bases, but mostly weak, and using our weak equilibrium methods. So, in your notes, as it says, I have no idea which page in your study guide we're on, but you do. So, we're going to be looking at weak base problems, and we're going to be using KB, the base constant or equilibrium base constant for weak bases. So you guys were working with KAs the last two classes, so now KBs. As it says in your notes, the patterns for solving KB problems are identical to KA that we learned last class. The big difference is they always give us the pH, and pH isn't really useful for bases. We need to convert it to the pOH. So that's sort of an important step. In any of these problems, as soon as you're given the pH, turn it into the pOH. Why? Because then we can get the concentration of hydroxide. And once we have concentration of hydroxide, we have X in our ICE tables and X in our shortcut. Okay, so we're just going to take a look at some problems and learn as we go. So first one, student measures the pH of a 0.250 molpiliter solution of aqueous ammonia, and hopefully you would recognize that ammonia is a weak base. If you don't, the fact that the pH is 11.32 would be a little bit of a hint that it's a weak base. And you could also go searching on your table of relative strengths, and you would find ammonia right there in the conjugate weak base column. So you have a few clues or ways to figure out that this is a weak base. Okay, calculate the Kb for ammonia. So to calculate Kb for ammonia, let's show its reaction first. So it is a weak base. It's just a solution of aqueous ammonia, so that means it's just sitting in water. And as a weak base, Bronsted-Lowry says that it will accept a proton. So that means water is our weak acid. And because it's a weak base in water, it's stuck in weak equilibrium, less than 50%. We don't know the exact percent, but we know it's less than 50. And our products, NH3 gains an H+, so it becomes NH4+. And water lost an H+, OH-. So that's why ammonia is a base. It produces hydroxide ions. And because it is a weak base, it will also have a conjugate acid. And water, acting as our weak acid, has a conjugate base. Okay. So we need some numbers here. What are we doing? We've got an initial concentration of 0.250. Water is a liquid, has no concentration, so we ignore it. And initially, we don't have any product, but as soon as this stuff hits water, it starts to react and it moves forward. So a small amount, which means we're going to lose 1x, or one amount of ammonia. And these are all 1-to-1 ratio, just like the weak acids. So we're going to gain 1x, gain 1x. So when we add the top two rows together at equilibrium, we will have 0.250 minus x, 1x, 1x. Okay. Now we have x. How do we have x? Because we have the pH. If pH is 11.32, we can immediately convert that to pOH of 2.68. And if we have the pOH, we can get the concentration of hydroxide, or the value of x, by going 10 to the negative pOH, or 10 to the negative 2.68. And that is 0.0021. Lots of decimal places. Okay, so we have x. Now to calculate the Kb value, we write out our equilibrium expression. Kb is equal to concentration of products over reactants. And these are equilibrium concentrations, and we have these values because we have x. So it becomes 0.0021 squared, because these are both 0021. Okay, And NH3 is 0.250 minus 0.0021. Put that whole thing in brackets, plug it in, and you get a Kb value of 1.8 times 10 to the minus 5. So if we put that over 1, we can say that it's always products over reactants. And we would say that this favors reactants. One reactant for every 0.000185 products. So it definitely favors reactants, way less than 1% product. And that would be typical for a weak base. So just a little review of those key ideas. So for a weak base, the useful things are we have to turn pH into POH because that will allow us to get the concentration of hydroxide, or X. And we're calculating for Kb, not Ka. And another point will be coming up in a minute. Okay, awesome. Let's move on. Any questions? There's never questions. This is what sucks about online learning. You never get to ask a question, at least not easily. Email me, which takes forever. I know, frustrating. Okay. The second type of calculation involving a Ka value allows you to predict the pH of any weak base solution. So we can predict pHs. We're not given pH, we can figure them out. So you use the initial concentration of the base and the Kb to determine the equilibrium concentration of hydroxide and then hydronium. Oh, it's a lot of information. Okay, the twist is that you are never given Kb values. Okay, never given Kbs. You have to figure them out yourself or convert them from Kas. It's a very easy conversion. And it's kind of interesting. If you take a Kb value for a base and the Ka value of its conjugate acid, so we go base and conjugate acid, and you multiply them together, you always get Kw. Isn't that interesting? Their product is always 1 times 10 to the minus 14. So if we rearrange that, you can solve for any Kb for any base if you have the Ka of its conjugate acid. And we do, because we have this table that has all of these acids and their conjugate bases. So every acid has a Ka. So if I have the Ka, I can figure out the Kb of this base. If I have the Ka of NH4+, I can figure out the Kb of NH3. If I have the Ka of hydrogen ascorbate ion, I can figure out the Kb of the conjugate base. Okay, so the example that they give here is, what is the Kb of the dihydrogen citrate ion? Okay, that one. So if you look in the data book, we have the acid, and we have the conjugate base, and we have the Ka of the acid. And in your data book, it's right here, citric acid, right here. So there's the acid, and there's its Ka. And we want the Kb of that base. So we use our handy little converter, Kb equals Kw over Ka of its conjugate acid, which was 7.4 times 10 to the minus 4. So plug that into your calculator. 1 second exponent. Negative 14 divided by 7.4 to the negative 4. And we get 1.35 times 10 to the negative 11. And we only have 2 sig digs, so it's 1.4 times 10 to the negative 11. So that's the Kb of the base based on the Ka of its conjugate acid. Okay, so that's trick number 1 to these questions. If you're given a base, you got to figure out its Kb from the acid. All right, so let's try a realistic question. Solid sodium benzoate forms from a basic solution. Forms a basic solution. Dissociate. So sodium benzoate is made of Na. So benzoate is C6H5COO minus. So there's our, when that dissociates, that's an Na plus. and this is a C6H5COO minus. Now this stuff forms a basic solution, so which of these two do you think is the weak base? As always, it has to be an anion. The only weak base that's not an anion is NH3. So the rest of them all have a negative charge. So let's show the reaction first. That's a 5. So like every weak base in water, this will accept a proton to make our hydroxide, and this becomes C6H5COO. Gained an H plus, so it lost its minus and became H. Charges are balanced. We have -1 on the reactants, -1 on the products. Those water's neutral and that one's neutral. Okay, so there's our Bronsted-Lowry equation. Okay, and this is, so dissociate it, write the chemical equation for the weak base in water, and determine the Kb. Okay, so Kb of this weak base is equal to Kw over Ka of its acid. So this is the weak base, and this is its acid. So we're going to go searching for that one, C6H5COOH. C6H5COOH. Here it is. Okay, so there's the acid. We're interested in the Kb of the weak base. So there's the Ka of the weak acid. 6.3 times 10 to the negative 5. Okay, and you plug that into your calculator, and you get 1.6 times 10 to the negative 10. Okay, so there's the Kb of the weak base using the Ka of its conjugate acid. All right, just picking up those skills, fast and furious. Okay, find the hydroxide ion amount concentration, so the moles per liter amount concentration of OH minus. Find the POH, find the pH, and percent reaction, holy smokes, in this case it's ionization, of 0.120 mole per liter solution of baking soda. Okay, so baking soda is, if you don't remember it, most of you would, sodium, hydrogen, carbonate. So that's an ionic compound, so let's dissociate it first. Na plus, HCO3 minus. Okay, so there's our weak base anion. When this ionic compound dissociates in water, the HCO3 minus is our base. Okay, so I'm just going to show how that acts as a base. HCO3 minus in water accepts a proton from some of them, a small percentage, to make H2CO3 and hydroxide. So there's its conjugate acid for the weak base. Okay, find Kb. Okay, find Kb. Kb equals Kw over Ka. Here's our conjugate acid, H2CO3, so we have to go look that one up. H2CO3 is right here. Okay, there's the acid, so we need the Ka of its acid. 4.5 times 10 to the negative 7. All right, so that gives us 2.2 times 10 to the negative 8. Oh my gosh, what happened to that one? Times 10 to the negative 8. Okay, so that's the Kb of the weak base. So this guy, we now have its Kb because it is a weak base, 2.2 times 10 to the negative 8. Okay, find the hydroxide ion amount concentration, POH, pH, percent reaction. Holy smokes. Okay, all we know about this thing is we now have its Kb, and we know that it's 1.20 moles per liter. So I could set up an ice table. I'm going to switch colors here because this is going to get messy. Okay, I could set up an ice table, ICE, and we would be starting off with 1.20, none of that, 0, 0, we're going to lose x, gain x, 1.20 minus x, x. Now that's really messy, and the reason I only squeeze that in there is just to show you about where the shortcut is coming from. So remember, for weak acids, we say Ka is x squared over initial minus x. Every weak acid, they're all 1 to 1 to 1 to 1 ratio. Same thing for weak bases. So for every weak base, we don't need ice tables anymore. We can just go at the equilibrium constant. Kb is x squared over initial minus x. It's the same for every weak base. They all end up with this same values for their equilibrium concentration. X for the products, x squared, the initial minus x for the reactant. Okay, so we solved for Kb already, 2.2 times 10 to the minus 8, and we need to solve for x squared, and our initial is 1.20 minus x. So there it is. Graph it and solve for x. And remember that once you have x, we have our concentration of hydroxide. So when you graph it and solve for x, you get x equals 1.6 times 10 to the negative 8. Whoops, try that again, times 10 to the negative 4. And that is our concentration of hydroxide. Okay, so now the question asks us to find pOH. This is a long question. That's why we saved this chapter till last. You need all these Chem 20 and Chem 30 skills to put together at the end of the course. Okay, pOH is negative log of concentration of hydroxide. Okay, so negative log of 1.6 to the negative 4. 3.76. 3.76. 2 decimal places for 2 sig digs. Okay, pH is 14 minus pOH, which will be 10.24. Okay, hopefully I'm doing all this. I didn't have it all pre-calculated, but anyway, I'm sure we're good. Okay. If not, Casey's going to let me know if I got it wrong. Okay, pOH, pH. And then the last one, which we haven't done for a while, was percent reaction. Okay, so we produced 1.6 times 10 to the minus 4 as our concentration of hydroxide. So what is our percent reaction? So we made 1.6 times 10 to the minus 4 moles per liter. Out of a possible, we started off with 1.2. So if we had 100% reaction, we'd get 1.2 moles per liter of product. We didn't. We only got 1.6 times 10 to the minus 4 out of a possible 1.20 moles per liter. Then we need to turn it into a percentage, so times it by 100%. Okay, so that's the same. I'll just go... I can't carry all my digits through, so I'm just going to round this one for simplicity. 1.6 times 10 to the negative 4 divided by 1.2 times 100%. 0.013%. Wow. That is not a very high percentage of reaction, which tells us that HCO3 minus is a fairly weak base. Okay, and yet it even sits here in the table. It's in the bottom half of the table. So that's whatever. It's right near the middle, even below the middle. So that's what a weak base looks like in water. pH of about 10 and a percent reaction of less than 1%. Wow. Okay. So that question had a lot of steps, a lot of skills. Holy smokes, I hope there's not many more like that. Okay. So the next thing we need to look at is you have to be able to recognize and determine for amphoteric entities whether they will act as an acid or a base. And if you forgot what amphoteric means, this is compounds that have a proton and a minus charge. What does that mean? What is that all about? So that means that they can be both an acid and a base. So this one could act as an acid to make H3O plus and X2 minus. And this one could act as a base and steal a proton from water to make hydroxide and H2X. So they are weak acids and weak bases. They have a proton and they have a minus, at least a minus one. So which one of these is going to predominate? If I put HX minus in water, does it donate a proton or accept? So there's two ways to figure it out. A quick, easy way is to look at their relative position on the table. So I'm going to give you an example of HCO3 minus. Okay, here it is as a weak acid. It is 1, 2, 3 away from water. And water is the weakest acid. So HCO3 minus is a very weak acid. As a base, it is about 8 away from hydroxide, which is the strongest base. So I can just see by relative position that this is a stronger base than it is an acid. Look how far it is away from water. We're going way up here to get to water. So there's water, and it is way down here. So that's a relative position way. If you're a numbers person and you like numbers, then you do it this way. You compare the Ka of the acid, so we'll call HCO3 minus a weak acid, and its Ka is 6.3 times 10 to the negative 8. So now we have to figure out the Kb of the weak base. And the way we do that is Kw over Ka of its conjugate acid. And the conjugate acid is, whoops, I gave you the wrong one. Sorry, we're not doing HCO3. This example says H2SO3. Let's do HCO3 minus. This one I'll leave up here and you can look at after. Okay, except I have the wrong value there. Oh, I'm messing this one up. Okay, so the Ka of HCO3 minus. Let's go look that one up. Here it is. The Ka of HCO3 minus is 4.7 times 10 to the negative 11. 4.7 times 10 to the negative 11. Okay, now we need to get the Kb of HCO3 minus. So we look in this column. Whoops, it is right here. So we're going to use its conjugate acid, 4.5 times 10 to the negative 7. Okay, 1 times 10 to the negative 14. Divided by 4.5, negative 7 is 2.2 times 10 to the negative 8. Okay, so if you're a numbers person, we compare the Ka of the acidic form to the Kb of the basic one. Whichever one is larger is stronger. And that would be negative 8 is a much larger value than negative 11. So its Kb is stronger, or larger is a better word. Kb is larger, so stronger base. And the example on this screen is for HSO3 minus. So I don't need to go through it, but you can look at it. There's the Ka of HSO3 minus. And you calculate the Kb using its conjugate acid, and you discover, well, you can look at it. It's all here. I don't need to go through it. I've got an example with you. Oh my gosh, why is that not erasing? Okay, so that is an example of the two different types of weak bases where you are given the pH and you have to calculate the Kb value using a Kb equals x squared over initial minus x. So basically, using our shortcut, I can give you Kb value and I could give you initial concentration and say solve for x. And why would you solve for x? Because you're trying to find the pH. And you would do that by getting the pOH and then the pH. And that would all come from concentration of hydroxide. So that's question number 1. Question number 2 is, I could give you the concentration of hydroxide. I wouldn't give you that. I'd give you the pH, and you'd turn it into pOH, and then you would turn that into concentration hydroxide. And I could give you the initial and say calculate Kb. So in this one, you're solving for X. This one, you're solving for Kb. And using those big, beautiful brains of yours, can you tell me the third thing you could be asked to solve for? That's right, the initial. So I could give you Kb, I could give you pH, and then say, what was the initial concentration? So again, all 3 of them, you're given 2 of the variables, you solve for the third, you can use the shortcut every time. And just to review, you do the same thing with the Ka for weak acids. So every weak acid, as soon as you recognize it's weak, it's x squared over initial minus x. And you would go from there. Now, I don't think I talked about strong bases today. I feel like I missed that. So I'm just going to scroll back here, give myself a slap in the side of the head, say, what were you thinking? Why didn't you go through a strong base problem? Okay. So strong bases, how would you recognize them? I can't believe I missed that. So strong base is an ionic hydroxide. So calcium hydroxide, sodium hydroxide, potassium hydroxide, there's lots of them. You'll never see these guys, so I wouldn't worry about them. Okay, so you dissociate them 100%. They're high solubility ionics. 2 mole per liter would give us 4 mole per liter, because if you look at the stoic, CaOH2 dissociates into 2 hydroxides. So that means we would go times 2 hydroxides for every 1 CaOH2. So that's where the 4 mole per liter would come from. So once you have 4 moles per liter, you could figure out the pOH, negative log of 4, and then you could get the pH as well. So that's what strong bases look like. It's just stoichiometry. And then for our weak bases, we are using the equilibrium expression, and we are jumping straight to that wonderful shortcut. And we know that X is equal to concentration of hydroxide. Okay, sorry, I should have introduced that at the start. I'm going to call this lesson a small flop. Jumping around, a little scattery. I'm only getting 2 hairs out of 3. Okay, so jumping back down to the end and make you guys seasick. Okay, so that's weak bases and weak acids. Same thing. You can solve for Ka, or you can solve for X. And remember that for weak bases, X is concentration of hydronium. Or you can solve for initial. There's always data given to get 2 of the 3. Okay, so you will always have 2 of 3. Now, why am I telling you this? Why am I doing this review? Because this is the last big assignment on all of this equilibrium stuff. So it's in your study guide. It's called Strong Acid, Strong Base, Weak Acid, Weak Base. So it's all 4 types of problems scrambled together. And as it says here, the correct answers are on the back, not the solutions, just the final numbers. So you try the problems, see if you can get the correct answer. And if you're totally stumped, we'll have a Google Meet this week and we'll go over them, any of the toughies that you can't get. In theory, you guys should be able to look at any acid or base and decide, is it strong or weak? And if it's weak, then you're going to go use the shortcut. And if it's strong, you're just going to go stoich. 3 moles per liter becomes 3 moles per liter. And that's for both acids and bases, same pattern. So really doing this worksheet is critical to your understanding and success of this the last sort of 3-4 days. My goal is to get you to be able to do all these problems, and it's a mixture of all 4. So it's a little tricky. So you have to look at it, and if you're not sure, you can go look on your data book and see if you can find it as a weak acid, a weak base, a strong base, or one of the big 6 strong acids up here. Other hints that you'll see are if you are given a Ka or a Kb value, that's telling you it's weak. And sometimes you have to use the pH to help you. So if your pH is like 3 to 6, or let's go 8 to 11, that's probably also weak. It does depend on concentration, but as a rule, those are your weak acid and weak base pH ranges. And if you're given a Ka or Kb value, it's weak. So those are hints, as well as using table of relative strengths. So a lot of talking. When you start those questions, first thing you ask yourself, is it strong or weak? Is it acid or base? And then that tells you where to go from there. You may struggle a little bit on this assignment. It's one of the more challenging of the course, without a doubt. This is where you put it all together. Impress yourself. Go for it. Be tenacious. Show a little perseverance. If you're struggling, leave the question, come back to it, try the next one. Phone a friend, send me an email, wait for that Google Meet, but don't just give up if you get a third of the way through and you're not getting them right. Keep going, keep trying. Eventually you'll get a few, you'll get some success. If you have to go back and watch the videos the last 2 days, that's okay too. They're there for you. Tomorrow's a rainy day. So no, not tomorrow. This one's Wednesday. We just had our rainy day. Anyway, good luck. Okay. Take care, everybody. And we'll talk soon.